and hoping you would understand it. And then I realized I wasn't recording shit. So my apologies on that front. So I'm gonna have to explain this like again, which is fine with me. I can't believe I did that to myself. So first off, I need to talk about the structure of the overlapping field of what is machine learning, right? And this is the beginning of machine learning topics. So the first thing I was talking about is that it's data science. At the end of the day, that's the big bulb. What is data science? Well, it's really just a major, but I mean in UCSD. But in reality, if you think about it, it's a big amount of data, right? And it's a discipline really, using scientific methods and algorithms to extract some knowledge and insight in area. This is what it's saying, and artificial intelligence goes into that. Artificial is the theory, and computer system is so that we humans, there's normally human intelligence needed, but instead we're using a computer to do it. Machine learning is a computer with the ability to learn, and starts the ability to start doing some coding. There's some statistical foundation here. This is in between over here, and this in between over here is what I like to call what people like to call, not just me, it's a statistical foundation. This is a statistical place that you'll see later on. But for now, that's all you need to know about that place. And then deep learning is a deep learning algorithm using neural network. Now this is where everything is, and there's some this is where everything really starts to make in. But there's going to be an input like this, and then you're just going to say neural network over here, and there's going to be an output over here. Oh, again, a lot of this thing is what I got from this professor over here. If you want to read them up, you can. But I'm using a lot of his notations to explain everything to you. Anyways, we begin with supervised learning, which has a learning map, which kind of shows over here like this learning map. Now, unsupervised learning has no label or data. Reinforced has a system interaction environment, which gives rewards. We will talk about later. An example of supervising learning is regression and classification. Unsupervised learning is clustering, interdisciplinary anomaly detection, and associate learning. Reinforcement is control and gaming and cue learning and deep reinforcement learning. But we'll talk about all of them if we need to or have time. Supervising learning, so I said regression line, as you can see over here, you see over here, the M over here into a lot of points over here. That is our data set, fine mapping, and so on. And over here, we see the X and Y, which I have labeled X1, X2, X22, and then 3, 3, and then 4, 4 to MN. And over here, we see that there is a grid over here, and this is take an image over here. You can do RGB, green, red, blue, green color spectrum with numbers, or we can do a grayscale. Either one, there's really good research done in the brain with the grayscale. So either one really needs to be looked at. I mean, it has some applications. You can see over here. This is the brain image. So there is some applications here. There's also machine learning out of the material science world, which is quite common actually. You can see all over gradients and something else. Unsupervised learning creates clusters, and I was trying to describe clusters of information like this, which is interesting. So this cluster, and this is like manifold learning. You'll see that later on. But there's a 2D projection and an unrolled manifold projection. You'll see later on. And this is actually a lot very mathematical, and you see what I'm talking about. And there's a linear, there's a idea of a feedback with the image software. Linear clustering is also true with the image. What I mean by that is like imagine something like you have a data set like this, and you see a bunch of things like this, and you can kind of see a pattern like this. There's some linear clustering you can do. Unsupervised clustering examples are linear clustering. That does happen though. It's not abnormal. Oh, okay. And then there's training, collect data, feedback loop. Like there are strategies of collecting data and going to training and collecting data again and improving the strategy and then the feedback to self-improve like crazy. That should not be surprising, as that's kind of how a lot of things operate in the case of machine learning. I do want to say something about the physics though, which is a very important thing in my opinion to talk about. Actually, first we talk about the roadmap. Is define the problem, collect data, design, train model, test model, go back to design model, and then deploy model and monitor and maintain, and go back to collect data. There's a loop over here, which that is what we call supervised learning. You could take that as a good thing, a bad thing is your choice. I think it's a good thing. It's a good thing that we have a structure. But over here, we go to big data over here. We have some data over here, and we have small data over here. Now that's the loop. So small to big over here. This arrow shows what goes to small and big. But the need for physics is going the opposite way. Where over here there's no physics needed, and there's some physics needed, and there is a large loss of physics. I think they wanted over here. We do not want to get into a state where there's the machine learning goes into nonsensical mode where it goes into no physical law matters. That sounds insane, and I don't think that is a really good, yeah. Anyways, we need to look at probability fields too. I'm sure you have been taught probability fields so many times through your academic career. Again, there's a random variable. A random variable is a variable that can take a different value randomly. It is a numerical value whose specific value cannot be predicted with certainty before the experiment. So random value, right? X, we can really see this as a probability distribution, which I think we have seen a lot. This thing over here, right? That's a probability distribution with the fx, but I think there's a lot of ways to write this. A lot of people think in the probability field sometimes like to write it like this, where we have like something like this going that way, which sure, I don't, it doesn't really matter, but in reality, it's in the real case over here, we have a real um, once again cumulative distribution function. We have something like points, right? Like this, point, 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 right? And then we so far go do that. This is what we call the cumulative function is defined with probabilities of variable that's also equal to the argument, yeah, so forth, so forth. So yeah, and you already know that the area under the probability distribution curve is one, has to be. That's been taught to you since like first year of college continuously. It's the first one thing that you keep getting drilled in your head all over your university life, because probability is a very tricky thing to learn sometimes, in my opinion. Anyways, here's an interesting question. What's the probability? And this is going to be a really simple question, actually. Probability at x equal x is going to be equivalent to saying what? Is it? I said the area under the curve is one. So at a single point, what is it? Is it an integral? No. Is it a finite differential dx? No. Is it the number between 0 to 1? No, it is 0. So that's a little tricky. That's what so it's equivalent to saying 0, which is interesting. Not sure if that will be equivalently valuable to you, but it's an interesting fact that you can take it whatever place you want. So joint probability density function also exists in the x and y direction, and then you can take integral in x and y to figure out the whole thing. And then there's certain other property functions where you do double integral. So this is where we actually get into probability mixed with calculus. So you never really thought of this, and I'm pretty sure your entire in your when you were taught. This is a probability section that wasn't taught usually, but you have something like this, right? A 3D like some kind of function. So this 3D kind of thing is equivalent to say integral. I believe is if you want a certain like 2D section over here, integral like if you want everything is integral to infinity, but this is a f x y u comma v dv dx over here, and that is what we call uh, well, that's not. Well, that's like doing integral in 2D. So in 1D, this would equal to. Well, this is also equal to 1, by the way. The integral. So what I'm saying is it's 100% if it's 1. So it makes sense it'll be 1. Let me just rewrite this a little bit more cleanly because that was a little messy. So instead of doing the whole thing, what would be the integral of the whole thing? Well, that would be. Let me just write this a little bit clearly. Infinity, negative infinity, infinity, negative infinity. That would be f x y x comma y dx dy. And then that would be equivalent to saying 1. So that's a powerful tool you can use whenever you want. And then there's also obviously the derivative. You can do it in both directions. I'll give you a contour and the direction. You can do whatever you want with that. There's also the idea of marginal probability distribution of x. This is an integral just in the x direction. So you're going to take it. So you're trying to figure out the probability distribution of x. So it's going to be f of x you're trying to figure out. And to do that, you take the integral of the full thing and get rid of the y. So what I'm trying to say is if you're trying to do that, you're going to do this. Basically negative infinity, f x y, x comma y, dy. That's all you're going to do, and that is true. So, and there's a lot of different things with marginal probability you can do, and then contours with that, but that's more probability. And that in that case, I think I do have to talk to you about it because you probably don't know about this. Like, do you know about that's marginal probability right there, and you can do the x y version if you want easily. There's also the conditional probability, which is a little bit more tricky, and we'll go through that next time because I'm out of space here. It's actually just a function that you will think. But yeah, this was we're doing machine learning a little bit here, and hopefully next time I don't have a problem with recording it because I wasted an hour on this now. Actually, we'll just finish the conditional probability a little bit. Conditional probability is basically saying x is equal to x, y to y. So saying it's conditional on something else too. So it's a conditional or given. So and then it will be p x equal to x, y equal to y. So it's capital Y divided by p x comma y. That's what it's saying. And Visually, what that means is you're getting a 2D function, you're getting a 2D image in the one side. So you're getting image this way, which shows you a contour like this. Excuse me, and you're doing a contour like this to show this thing off, and you're doing a contour like this to like something like that. It is a contour shape. It's showing a contour and doing a 2D projection on both sides and then showing it off. And then what's left with is this side over here, which is y1. Great, right? That makes sense? So if x and y are said to be independent random variables, if for all y, then you could claim a lot of things actually. Too many things to count, but that's probably for you. It's too much to even think about. Uh, yeah. So next time I will go over, I think we're on to gradients now. No, no, there's still more probability and eventually more probability. When do we go start doing linear regression lines? Way later, we'll start doing the MN's whole speech. Oh, and I did do a typo over here. This is supposed to be a 1. Y1, X1, that makes more sense. And then we're going to talk about Newton's methods, and I'm going to be getting the J prime equals 0. J is a cost function, which is defined by y, 1 divided by m summation y. And then we're going to talk about 2D projection. If we have time, we'll talk about a little bit about starting to talk about matrices with different interpolation schemes with different matrices. Hopefully we get to there. But if we don't, then we don't. We're going to end it here and have